This is a tutorial video on time in astronomy. I'm going to use the planetarium program Stellarium here to demonstrate a few things about how we use time in astronomy. There are a few different topics I'm going to cover. I want to talk about local apparent solar time or sundial time, local mean time, standard time and time zones, Julian day number, and finally local sidereal time or local star time. Now, to start talking about this, first I want to solve a mystery. It's a common misconception that the sun is directly overhead at noon. That can actually only happen in the tropics, and here in New Haven at latitude 41 degrees north, we can never see the sun directly overhead. It's just a couple days past the solstice right now, which is when the sun is highest in the sky at noon. And there's the zenith right there. That's 90 degrees altitude. And there's the sun right there. If I click on the sun and look at its altitude and azimuth, its altitude is 72 degrees in 6 minutes. And then its azimuth is 180 degrees almost exactly. So the sun is almost exactly due south right now. It is true, though, that it is local solar noon when the sun is on the meridian. So when the sun is due south, it's at its highest point in the sky. It's midway between sunrise and sunset, and that is local solar noon. So if it's local solar noon, why does my computer clock here, my settings clock, read 12:54 and 6 seconds? That's what I have here in my date and time window, 12:54. Shouldn't it read 12:00:00? I can see, for one thing, my time zone is set for UTC minus 4 hours. Normally, so New Haven is in the Eastern time zone. Normally, we are 5 hours behind Greenwich Mean Time. But in the summer, we're on daylight savings time, and so we're only 4 hours behind Greenwich time. So it's a little bit closer to 1 o'clock at local solar noon than 12 o'clock. If I were to actually go to 12 o'clock Eastern Daylight Time, you see the sun is way to the east of the local meridian. It's anti-meridian or AM. Let's first fix that problem. Let's turn off daylight savings time. Now, the easiest way to do that in Stellarium is to go into the configuration window, and there's a plugin for Stellarium. It gets installed automatically, although you may have to load it at startup specifically. This is the time zone plugin. We go to configure. By default, it says use system settings. So when your computer is set to daylight savings time, it uses daylight savings time. Standard time, whatever, it'll change for the way the computer would show time given your latitude and longitude. Another option would be universal time. I'm going to say offset from UTC, and I'm going to set this for Eastern Standard Time, like so, and then I'll say save settings. Now, any changes will take effect the next time Stellarium is started, so I need to quit Stellarium, and then I'll relaunch it. Here we go, and I'm going to turn on the meridian again, so. And I now have UTC minus 5 as my clock. So let's go to today at about noon, and there's 11:59 and 0. All right, and let's see where the sun is. Now, the sun is a little bit to the west of the local meridian. Local solar noon happened a little bit earlier. So being in the right time zone doesn't solve the problem completely. So let me think about this a little bit more. The time zone, the middle of the time zone is at longitude 75 degrees west. And my latitude and longitude here in New Haven, I'm at 41 degrees and a third north, almost 73 degrees west. So I'm about 2 degrees of the east of the center of Eastern Standard Time. So let's fix that. So we'll just go to 75 degrees west. There we go. And I'm no longer in New Haven. I'm on Earth at latitude 41 degrees north, negative 75 degrees. So that's 75 degrees west longitude. things are looking up. Things are looking better here. Let me set this to noon. And let's actually stop time here. And let's see where the sun is now. It's still a little bit behind the meridian. So the sun is a little bit slow compared to Eastern Standard Time at 75 degrees longitude. And you can see that also over here in the azimuth, 178 degrees. So the Earth still needs to turn approximately 2 degrees, a little less, for the sun to be on the local meridian. Well, what's going on here? Well, the problem is that sundials, which try to measure the hour angle of the sun, are not very accurate. They can be up to 15 minutes fast or slow. Hour angle, by the way, is just the angle between an object and the meridian. So if the sun were right on the meridian, which happens right about there, about an hour later, the sun would be 15 degrees to the west of the meridian. So we'd say its hour angle is plus 15. 2 hours later, its hour angle is plus 30 or plus 2 hours, 30 degrees or 2 hours. And then hour angle can also be negative. So there's negative 1 hour or negative 15 degrees, negative 2 hours, and so forth. So hour angle is important for measuring positions relative to the local meridian. So the sun is a little bit wrong. I'm going to set this to 0, and I want to see just how bad the effect is over the course of the year. So there you see the sun's a little bit slow compared to my clock. And if I step through every day in the year, you can actually see, oh, there the sun's even worse. The sun's even more slow in July. And I can keep stepping through here, and you see there's the sun's getting actually closer to the meridian at noon. Here's a day in September when actually it's very close to being on the meridian at noon. Keep going. You see it's getting lower in the sky because of the declination, the changing declination of the sun. Here I am in October. Now the sun is fast. My sundial would be fast by, I could see how many minutes. Looks like it's approximately 15 or 14 or so minutes fast. So that's an extreme point. All right, let's go back to 12 o'clock. All right, and let's keep going through the year. There we're getting into the winter months when the sun's very low in the sky at noon. And here we are getting close to the solstice. There we are on the solstice, right? The sun's very low in the sky at noon. And we can keep going. Now the sun is slow. This is in January. The sun is slow. And just keep stepping through the year until we get back to June. The sun's getting higher in the sky now because we're in the spring. The sun is still slow. And there, the sun's on time. In April, the sundial would read the same as your watch if you're at 75 degrees west longitude. And then now we're getting back to the summer solstice, and the sun is a little bit fast. And getting back to the summer solstice, here we are. The sun's just a little bit slow. So this is a well-known effect. There are a couple of reasons that this happens. Number one reason is that the Earth is not in a perfectly circular orbit around the sun. So as the Earth orbits, sometimes it's closer. It's actually closest in January. Sometimes it's further away. It's furthest away in July. And so that affects how the sun actually appears to move in the sky. I'll talk about that when I talk about sidereal time. So that can explain why the sun is fast or slow on a yearly basis. Another effect is that the tilt of the Earth's orbit means that the sun, as it takes its path around the sky, sometimes it's going due east, like near the solstices. Sometimes it's heading sort of east and south. That's near the fall equinox. Sometimes it's heading east and north. That's near the spring equinox. And so it doesn't always move exactly 1 degree to the east around the celestial sphere. So that has an effect also. So it turns out that if you're using a sundial to keep time, it will speed up and slow down by an effect called the equation of time. And we know what this delay or lead is for a sundial over the course of a year. There are 4 days a year when the correction is 0. December, sort of in the middle of June, middle of April, and then also here kind of towards the beginning of September. But here the sundial is See, this is when it's fast, and then this is when it's slow. And you can see it's almost 15 degrees in both directions in terms of the error. Now, how would you actually discover this? Well, if you have, a good sundial, this is a nice horizontal dial sundial. This is designed to work at a specific latitude and report basically the azimuth of the sun. As the sun goes from east to west, the shadow of the gnomon right here will move around, and this gnomon has to be aligned with the north celestial pole. So this angle here has to be equal to your latitude. A fancier sundial has a tilted dial like so. This is a sundial that's in front of the Adler Planetarium in Chicago. And this actually directly measures the hour angle of the sun, because this gnomon is in line with the north celestial pole, the axis. It's basically parallel to the axis of rotation of the Earth. And then this dial is parallel to the equatorial plane of the Earth. So as the Earth rotates, the sun rises in the east, which is going to be over in this direction to the right of the image. And the shadow would appear over here on the west side of the dial. And as the sun moves through 15 degrees of hour angle every hour, then the shadow from the gnomon is going to move 15 degrees. And it's not affected by the changing declination of the sun. So this is a nice design for a sundial. But if you compare a sundial time with some kind of accurate clock, which in ancient times they had things like water clocks. This is an ancient Greek style of water clock where you have water filling up a funnel and it drips out the bottom. You can even be more sophisticated, have a float that moves up that turns a dial. These can be very accurate if you control for evaporation. And later on, actually, clockmakers used liquid mercury, which we know today is not safe, but back then it was great because liquid mercury is heavy and dense and it doesn't evaporate. You could also use just an hourglass, right, full of sand. These can be accurate as long as they're sealed from the elements, so you don't have changing humidity in here, and you also the point of constriction here doesn't change with the temperature. Then hourglasses can also be fairly accurate within a minute or so. Certainly accurate enough to see that the sundial is speeding up and slowing down. Well, if you take sundial time, which is just the hour angle of the sun plus 12, so when the sun's on the meridian, its hour angle is 0, and add 12 to that, you get 12. So 12 o'clock is local solar noon. If you add on the correction of time for the particular day of the year, here it is plotted as a graph, but you can easily find tables that give you the correction factor for any day of the year. And all of these numbers are in minutes, and they're going to be accurate to a few tenths of a minute. You take your sundial, you add on the equation of time. Sometimes it's negative, sometimes it's positive. And that gives you a new time, which is your local mean time. It's a time that doesn't speed up and slow down over the course of a year. It's the time that an accurate mechanical clock would keep, ticking off seconds, 1 second per second, and not speeding up like a sundial does. So local mean time is important, and that's basically the kind of time that you want to keep. Greenwich Mean Time is specifically the local mean time for Greenwich Observatory near London, which is, of course, where the prime meridian is, which is the 0 degree reference line for longitude. So local mean time is perhaps what you'd want to set your watch to, but the problem is that every location on the Earth is going to have a different longitude, and if you go east or west, your longitude changes, and because of the curvature of the Earth, the sun will actually change its position in the sky relative to the meridian. So I go back here to Stellarium, and if I set up my my system for local solar noon, so let's put the sun right on the meridian. So there it's 180 and 29 arc minutes. I'll go back a little bit because I want to be even closer to local solar noon. I'm not going to get it exactly right, but let's get it within an arc minute. Okay, so that's good. So 180 degrees, the sun is on the local meridian, it's local solar noon. My local mean time, though, is 12:02:21. If I were to go look up the equation of time correction, it would be minus 2 No, I guess it would be positive 2 minutes and 21 seconds. If I jump 1 degree to the east or west, then the sun, if I jump 1 degree to the east, the sun will jump 1 degree to the west. And vice versa, if I jump 1 degree to the west, the sun will jump 1 degree to the east, and it will no longer be local solar noon. It'll be 1 degree of angle, which is actually 4 minutes of time different. So let's try that. So let's go now, let's say 1 degree to the west. So we'll go to a location window here, and we'll change this to 76 degrees. All right, and actually you saw the sun just jump immediately 1 degree to the east. Let's actually make it even 77 degrees. Make it 77 degrees. All right, and there you saw the sun jumped another degree. So because of the curvature of the Earth, your longitude is going to affect when you had a certain time, local mean solar time. If I now, this is still set for Eastern time, so this actually isn't going to change, but it actually should be 4 minutes. If I run forward 4 minutes, all right, then I get back to local solar noon. More accurately, I think it's 3 minutes and 56 seconds, so it could be a little bit more accurate there. This means that you can use your local time to figure out your longitude. If you know your longitude where you are, if you know the local mean time where you are, and you know the local mean time somewhere else, let's say Greenwich Observatory, then you can compare the two, and that tells you your longitude. If your watch says noon, Greenwich Mean Time, but your local mean time is 2 o'clock in the afternoon, you're 2 hours east of Greenwich Observatory, or 30 degrees east longitude. I have a separate video on celestial navigation where I do an example of trying to figure out where you are on the Earth using your local mean time, which you can get from the sun if you know the equation of time correction. Take local solar time, add the equation of time correction, that's your local mean time. Now, there was a time in the past when different cities would actually use local mean time, and local astronomers would measure this for them. So Washington, D.C. had local mean time, Chicago, San Francisco, all the major cities had astronomers calculating their local mean time. And if you came into the city on a stagecoach, you would go look at the public clock to figure out what time it is to know when you have your appointments. Of course, this is a big problem when the railroads start to expand, and you can travel quite quickly from city to city, and you want to know, well, what time is it going to be when I get there? If it's 12:20 in New York and I travel to Chicago, what time is it going to be in Chicago when I get there? So the system of time zones were instituted. So we sort of take the change in local mean time and spread it out over 15 degrees of longitude, so that we have the accepted time zones. So here's a map of the different time zones. You can see there's +0 for Greenwich and the Greenwich time zone, +1 for this part of Europe, +2 for 30 degrees over here for Eastern Europe, and so forth all the way around. Over here in the United States, Eastern time is -5 relative to Greenwich Mean Time. Central time is -6, Mountain time is -7, Pacific time is -8, and so forth. So pretty straightforward, yes? This map also shows how wrong the standard time is compared to local mean time. So if the color is red, then that means that you're behind your mean time, your local mean time is behind your standard time. And if the color is blue, then that means that your mean time is ahead of your standard time. So the middle of the time zone should be white, like so, and then east of that will be blue and west of that will be red. Now, some countries, such as Argentina, they pretend that they're in a time zone that's further east. So you see Argentina's clocks are all too fast relative to the sun. And the point of that is to have permanent daylight savings time. It's basically to force people to get up earlier. So noon on your watch happens before noon in the sky actually happens. And that's a choice that you can make. It's a political choice. We go on daylight savings time in the summer so that instead of in Eastern time zone being 5 hours behind, we're 4 hours behind. We pretend that we're one time zone to the east. So you can see Kazakhstan, parts of North Africa are also quite red. Africa is not really, Alaska is not really in the right time zone either. So that's something that's unusual. China, you can see, has one time zone. It's all at +8 relative to Greenwich. So most of the population of China is over here on the east side of the country. So they just made the political decision that everyone all over the entire country is going to use Beijing time. And that was just a political decision that was made. If you live over here in Western China, your clock is going to be up to 3 or 4 hours ahead of where the sun really is in the sky. Your clock might say 12 o'clock, but the sun might be 3 or 4 at hour angle minus 3 or 4. So there's 3 or 4 hours to the east of the local meridian. So that's the time zone issue. It also, even the borders of the time zones, they're not necessarily exactly 15 degrees wide because of local political issues. And especially over here at the international dateline, you can see it makes some crazy loops east, south, northwest in order to envelop particular countries that are politically affiliated on these tiny islands out here in the South Pacific. There are also a few places where the time zones don't change by an integer number of hours. So you see there's a time zone right here in Australia where they decided to go, okay, this part of Australia is 8 hours ahead, this part is 10 hours ahead, but this part is 9.5 hours ahead. And that's just something they do locally that you have to get used to. There are also a couple of little islands over here you can see, plus 10.5 hours, plus 11.5 hours. So again, that's the way it goes. In fact, the whole country of Afghanistan is 4.5 hours ahead. Iran is 3.5 hours ahead. And there are all sorts of little quirks like that. Actually, India and Burma also not on integer hour time zones. Okay, so that's enough about the time zones, local mean time, and local standard time. Let's talk about Julian day number. Julian day number is a very simple kind of time. Astronomers love it. In Stellarium, you can see it over here in the date and time tab. There's this option, Julian date. Julian date is just the number of days that have passed since a reference point. Let's see when that reference point is. If I set this to 0, then that is 4,712 years before 1 AD. That would actually be 4,713 BC because there's no year 0. January 1st, and then 7 o'clock in the Eastern time zone. That's actually 12 o'clock noon in the Greenwich time zone. All right, that's weird. Why did astronomers use 4,713 BC as the reference point? Well, it's for obscure historical reasons. There are a bunch of cycles that get in sync at that point, and that was just the arbitrary starting point. But it doesn't really matter what day you use. If we jump back to 2016, let's change this to positive 2016. And let's pick July and July 1st. And let's pick sometime in the evening, like so. Right, let's say 8 o'clock in the evening. And if we look at the Julian date, all right, it's 245,751.55292. So you see that we've gone, well, more than 2 million days since that date in 4,713 BC. And if something happened tonight, if I measured the brightness of a variable star or the brightness of a supernova or the position of an asteroid, whatever, the convenience of this time system is I can record the time and not have to worry about the details of the Gregorian calendar. If I go from June to July, this date number, I have to remember, okay, well, there are 30 days in June, so now I got to add 30 to everything as I step forward days at a time. And then some years are leap years and some aren't. And so it can be tricky to compare when things happened at certain times when you're using the Gregorian calendar. And especially when you need to be more precise than just a day. So you need to know, okay, well, it happened at 8 p.m. Eastern Standard Time on July 27th, 2016, and then something else happened at another time. If you want to compare those two times, it's tricky because of all the different units and bases. Julian date is just days. If you need to be more precise than 1 day, you can use decimals. You can say a tenth of a day, 100th of a day, a thousandth of a day, and so forth. And so an hour is 1/24 of a day. So, that's 0.0 something days. So you can actually use these decimals to specify as precise as you need, a second, a millisecond, whatever. If I let time pass again, so let's let time pass, you can see how as seconds tick off, so seconds are ticking by right there, the number that's changing is over here in the 10 to the minus fifth, basically. So that's tenths, hundredths, thousandths, 10,000ths, 100,000ths. So a second is of order 100,000th of a day. So you can see that ticking off right there. And if we went through 24 hours, we'd come back to the same place, 0.5529, and so forth. Now, if you want to know what Julian date corresponds to a particular month, date, year, time, or if you want to know what Julian date, if you know that the calendar date and you want to convert to Julian date for astronomical record keepings, there are lots of ways to do it. You just need a reference time. You need to know, okay, well, what was the Julian date on a certain day and year, date and the year. And there are lots of, you can look that up and have that as a reference point. You can use a program like Stellarium to solve for it. You can also use various online Julian date calculators. The one that I usually use is actually at the USNO, the United States Naval Observatory. And so just go to this website. They will calculate for any given calendar date in the Gregorian calendar, including hour, minute, and second in universal time, Greenwich Mean Time, basically. It will compute the Julian date for you. And there are a lot of packages in Python and little algorithms that you can use to convert from one to the other. It's not trivial because the Gregorian calendar is complicated. Like I said, there are leap years and the months have not all the months have the same number of days, so you need a rule to convert from one to the other. But nevertheless, this is a useful way of tracking astronomical events in a continuous, linearly increasing decimal time system in units of days. Now, notice also Stellarium not only tells you JD Julian date, but it also tells you this MJD, what's called modified Julian date. It's basically the same, except they've subtracted off 2,400,000 and a half. So because Julian date starts at noon and a normal day starts at midnight, there's always this extra 0.5 if it's close to midnight universal time. So in modified Julian date, they subtract that off. There's really no reason to use modified Julian date. Astronomers generally just use regular old Julian date. All right, one last topic to cover in this video is sidereal time. On the face of it, sidereal time is very simple. Sidereal time is just the right ascension coordinate that's on the meridian at that moment. So if I turn on the equatorial grid, this shows me the grid of right ascension and declination, what I sometimes call celestial longitude and celestial latitude. So you can see those numbers over here. So the celestial equator is at 0, so it's that line right there. I can highlight it a little bit more clearly if I go and turn on the local equator. All right, so there's the equator right there. That's declination 0. And then you can see the right ascension circles up here. So there's 15 hours, 16 hours, 17 hours, and so forth. So the reason that astronomers use hours of time to specify celestial longitude is because as time passes, let's speed time up, a factor of 10, factor of 100, factor of 1,000. As time passes, different right ascension circles will cross the meridian. If you think of the meridian as an hour hand pointing right there at that point in the sky, if you look and see, okay, what right ascension circle is on the line, that's the local sidereal time. So there it is, 22 hours, that's about 22 and a half. That's 23 hours, 23 and a half. And then there's 0. So there's the start of a new sidereal day when that 0 point crossed the local meridian. Now, why would you care about what right ascension coordinate is overhead? Well, astronomers want to observe objects when they're highest in the sky. And so if you know the right ascension of the object and you know what is the local sidereal time, then you know how much time is going to pass before the object is on the meridian, when it's as high in the sky as it can possibly get. So for example, if I stop time here for a second, and I'll turn off the atmosphere so I can see the rest of the stars. So turn off the atmosphere. So let's see, there's the star. Actually, let me pick one over here on the east. There's the star Arcturus right there. And if I click on it, I get the right ascension and declination in these two different times. My grid here is for current precession epoch, so we'll go with this one. So 14 hours and 16 minutes. Well, what's the local sidereal time? Well, it looks like local sidereal time is just a little bit shy of 9 hours. We let just a little bit of time pass, like so. We get essentially 9 hours right ascension is on the meridian. So how much time between now and when Arcturus is going to be on the meridian? Well, I look up on my local sidereal time clock in my observatory. It tells me it's 9 o'clock. I look up the right ascension of Arcturus, which is 14 hours and 16 minutes. So the difference between those two is about 5 hours, a bit less than 5 hours. No, a bit more than 5 hours. So 1, 2, 3, 4, 5, and then 16 extra minutes. So I got to go 5 hours and 16 minutes for that's how much time has to pass before Arcturus is on the local meridian, and that would be the ideal time to observe it. That's when it's at its highest altitude. Now, why is sidereal time different from solar time? Well, the reason why is because, of course, the sun moves around on the celestial sphere. Its right ascension and declination change day after day after day as the Earth orbits around the sun, right? And the path that it's taking around the celestial sphere is just the ecliptic. Let me show you the ecliptic. So there you can see the sun's going around the celestial sphere along that red line. If I step forward a few days here, you can see its declination is decreasing there, and its right ascension is changing. So if you wait for one solar day to go by, let's put the sun closer to the meridian here. All right, so go back a couple of hours and back a couple of minutes. If I let one solar day go by, which I can do by just stepping forward one day, the sun will have also moved along the ecliptic by about 1 degree. So you see the stars drifting off to the right there relative to where the sun is. If I were to step forward by one rotation of the Earth, which is called a sidereal day, and I can actually do that in Stellarium by hitting Option Shift plus, like so. So that is, the Option key basically steps forward by a sidereal day rather than a solar day. I'm basically going forward one rotation of the Earth, and you see the sun is drifting off to the east as its right ascension and declination change, and the stars are coming back to the same place in the sky. So I'm stepping forward by one sidereal day, one 360-degree rotation of the Earth. That's not a solar day. It's not exactly 24 hours. It's actually about 4 minutes shy of one solar day. So a sidereal clock will actually tick faster than a solar clock, such that it goes through a sidereal day in a period of time 4 minutes shorter than a solar day. So sidereal clocks have to be designed to tick at a different rate. This is very confusing. Astronomy students are always confused about this when they first see it. It may help a little bit to look at the simulator that's on the University of Nebraska website. And this is designed to show you the difference between a solar day and a sidereal day, or solar time and sidereal time. So sidereal time is determined by what right ascension coordinate is overhead. So the celestial sphere is very far away compared to the Earth and the Sun here, but that's the direction towards 0 hours right ascension. That's direction towards 6, 12, and so forth. So when the 0 hour right ascension circle is overhead, then that is 0 hours sidereal time. And you can see the Earth rotates a little bit. There's 1 hour later, 2 hours later, and so forth. You can see the Earth rotating to the east. All right, I'll set that back to 0. When the sun is overhead, it's local solar noon. So here you see the solar clock is set for apparent solar time, and so there is 12 o'clock. And if an hour goes by, the sun is an hour to the west of the meridian, and so forth as we go all the way around. All right, let me set this back to 0 hours sidereal time. Now, what happens after a day passes? Well, let's say we step forward by 1 sidereal day. If we go forward 1 sidereal day, that's 1 rotation of the Earth. The Earth should come back to exactly the same place relative to this 0, 18, 12, and so forth. Well, as I said, that's 4 minutes shorter than a solar day. I have to go a little bit ahead to get to a solar day. But that's not really obvious what's going on in terms of the rotation of the Earth and the sun. So if I step forward by 10 sidereal days, we come back so that, yes, that we're in that same direction relative to the 0, 18, 12, 6. The little man is basically at the top of the Earth. But now the sun is no longer directly overhead, as seen from that little guy. It looks like it's about an hour or so, roughly an hour behind. Let's go another 10 sidereal days. And now it's even worse. Let's go another 10 sidereal days. On my sidereal clock, it's still 00 because 0 hours, 0 minutes, because I'm still lining up with the direction towards 0 hours. Now I've displaced a little bit, but you have to remember that the reference circle is really, really far away. So really what matters is where is the guy relative to kind of the background box that's around this whole thing. It's now earlier in the day solar time. It's like 10 a.m. solar time because you see a little bit more time would have to pass in order for the Earth to turn so that we hit local solar noon. So it's really the orbit of the Earth that makes the difference between sidereal day and solar day. If we go all the way around to the other side of the orbit, and in fact, what I'll just do is say, let's just run ahead to the set of the vernal equinox, the autumnal equinox. So here we are over here. All right, now it's 0 hours sidereal time. We'd look in that direction for stars that have 0 hours right ascension. But now it's midnight local solar time. So we've gone all the way around. So now you can see actually the clocks are in sync. So it's one day of the year that the clocks are going to be in sync because the sun has a right ascension of 12 hours. And then when it's local solar noon, like so, then sidereal time is 12 hours, solar time is 12 hours. So you see they're pretty close to being in sync. All right, well, that's my tutorial on different times in astronomy. That sidereal time is really useful for finding when stars are overhead. Local mean time is really useful for celestial navigation. But mostly we're going to use either universal time, Greenwich Mean Time, or Eastern Daylight Time, because that's the time that we keep on our watch. That's how we set appointments. If we say that class is going to start at 10 a.m., we're talking 10 a.m. Eastern Daylight Time, our local time for the time zone.